So hello everyone again and welcome to my channel. Quite fascinating because we're here looking at the Fourier molecular orbital in cycloaddition, and cycloaddition, which is really important in terms of choosing our diene and dienophiles and how these two species will be involved in cyclization to form products, which involves formation of sigma bonds from the breaking of pi bonds. But anyways, before going ahead, let's just focus more on the really molecular sense of how these reactions actually work. Now, there will be various rules that you need to apply, which are really important with what I use for me to actually successfully choose my HOMO and LUMO, because that is our end goal, and our end goal is to able to understand the combination of molecular orbitals whether in the HOMO or LUMO that will be crucial in the reaction process involving those two species. Now, my first rule I usually go for is that I need to understand and know where the conjugation starts and where does the conjugation end. Now, what do I mean by conjugation? Conjugation is quite interesting because in here we're looking at, for example, where is the break between the pi bonds and the sigma bonds, or most importantly, you need to know that in between pi bonds you must have sigma bond. So let's take for an example. We have butadiene, and butadiene, as you know, has this particular chemical formula or chemical structure, which is 2 pi bonds, right? So in here I have pi bond here, and in here I have my pi bond here. Take note that in between these pi bonds I have a sigma bond, which is over there, and the sigma bond is really crucial because in here you can be able to introduce flow of electrons, because all these carbon atoms have p orbitals that are perpendicular to the plane of the molecule. So remember, I have p orbitals too, I have plane of the molecule. So there will be a flow of electrons going from this particular region to this particular region, and from this particular region to this particular carbon. Or on the other side, I actually have the flow of electrons going in the reverse direction, moving towards this bond here and going towards this bond over here. So this is what we'll talk about in terms of the conjugation: a flow of electrons minimizing the energy level of this molecule, making it to be much more thermodynamically stable, and also quite important in the movement of electrons as it's reacting in this process of cycloaddition. Now, the next rule you need to apply is that you must recognize that the molecule is planar. And what do I mean by planar? Planar in the sense that if you recall the sp2 hybridization, and sp2 hybridization involves sp orbitals, which are 3, and one of the orbital which is unhybridized is actually the p orbital, and the p orbital is involved in the formation of the pi system of this particular molecule. Now, the sp hybridized orbitals are the ones involved in making that plane of the molecule. Let's say, for example, plane of the molecule in the sense that it forms the trigonal planar, and this is actually what we call the shape of the molecule. So looking at butadiene, we have butadiene with this particular molecule which is actually in the plane, and this plane has p orbitals that are perpendicular to it. So without going in further details, they just make all this to be in phase with respect to each other. So all these here are in phase with respect to each other, and once you're able to do that, then you'll be able to know that the plane of the molecule is perpendicular to the p orbital, and this p orbital are the ones that are involved in the pi system of this molecule. This is just one of the many that will be contributing to the structure or the molecular orbitals of this particular molecule. Now, moving into much more details, let's look at our final rule. Our final rule is that the number of the 2p orbitals that are present in the conjugating system are pretty much equal to the number of molecular orbital combinations. And these combinations are really crucial because in these combinations we'll be able to know which is our HOMO and which is our LUMO, where our HOMO is called the high, or I would say the highest occupied molecular orbital, and while our LUMO is called our lowest unoccupied molecular orbital. Now, the high is mainly called high because it is actually the highest energy level, and while low is something related to the lowest energy level. However, when you're looking at occupied, it's like when you're filling your electrons, the last region where you completely fill the electron is actually the highest energy last orbital combination where those electrons are filled, and while the unoccupied is where the next part is actually empty and is actually in the lowest region in that particular energy level where this particular molecule will be positioned. Now, let's look at this particular molecule, butadiene. Now, butadiene has 4 2p orbitals, right? And those 4 2p orbitals are actually the 4, or I'll just put bracket, 4 atomic orbitals that are present in this molecule. Now, these 4 atomic orbitals that are actually 2p orbitals, they will generate 4 molecular orbital combinations, and these 4 molecular orbital combinations includes the following. Now, first of all, I need to just make a relative scale, which is just the energy scale, and in here I'm going to have 4 different combinations that are crucial in this process. Now, if you're increasing in terms of the energy levels, what is the most important thing that causes this increase in the energy level? The most important thing that causes an increase in the energy level in this case is the increase in the number of nodes. So in this region here, I'm going to have number of node of 0. In here, I'm going to increase it to 1. In here, I'll increase it to 2. In here, I'll increase it to 3. So as we increase in the number of nodes, I'm going to cause an increase in the destabilization of those molecular orbital combinations that contribute to the molecular structure of this particular molecule. Now, let's start first by the lowest point here. The lowest one, if I don't want to have no nodes, then I'll make all of them to be in phase with respect to each other, where I have to shade these all up, or I shade all this down and leave that all up. So in phase. Now the next part here is that I'm going to make the number of node to be 1. So if I want to include 1, then I need to make it to be symmetrical in a way that at the middle there will be a node where the first 2 here are in phase with respect to each other. However, the second carbon and the third carbon here are out of phase with respect to each other, thereby causing atom bonding because they're both out of phase with respect to each other. But this and that, carbon 3 and carbon 4, are in phase with respect to each other. Now, moving over to the third one, the third combination will have an increase in number of nodes of 2. Thereby, between 1 and 2 carbon, I'm going to have a node there, and in between 3 and 4, I'm going to have a node over there. Now, 2 and 3 will be in phase with respect to each other, while 2 and 1 will be out of phase with respect to each other, and 3 and 4 will be out of phase with respect to each other. Now, moving over to the last combination over here. Now I'm going to make this last combination to have 3 nodes. Now, having 3 nodes means that all of them will be out of phase with respect to each other. So the easiest part to actually have to work with is the first one and the very last one, where the first one will be all in phase and the last one will be all out of phase. So let's just to the easiest one by shading this out of phase, out of phase, and out of phase. The node here. And this is just the simple case, because the simple case is just looking at the even number of carbon atoms that are actually 2p orbital, and those 2p orbitals will then generate 4 molecular orbitals. And even numbers are quite easy to work with. However, odd number carbon atoms are quite complicated a little bit, but you can look for a specific trick that will be helpful, and that will what I'll focus on my next video. So in here, once you're able to find your combinations, next is to be able to fill in our electrons. And in here, our number of electrons is equivalent now to the number of molecular orbitals. So in here, I'm going to have 4 electrons, and these 4 electrons includes the following. I have this gap here, energy gap here, and energy gap here. No form of actually degeneracy at all. They are all relatively higher with respect to each other. So since I have 4 electrons, first I'll put this down here, and then I'm going to pair this opposite spin, trying to obey the Pauli exclusion principle and the Haber's rule. And moving over to the next energy level, I fill that in, and then I pair it opposite spin with each other. Now, what are the conclusions that you can make from this over here? The only thing that are really important, mostly in cycloaddition reaction, is the HOMO and the LUMO state, and these 2 regions are really crucial in terms of Butadiene in determining which ones will be involved in the cycloaddition reaction in terms of its HOMO state and also in terms of its LUMO state. Now, this part here is called the HOMO because it is the highest occupied molecular orbital, while on the other side here is called the LUMO because it's the lowest unoccupied molecular orbital. And the energy gap between this and that is really important, because as you increase the number of conjugation system, the energy gap between the HOMO and the LUMO reduces at some point, thereby making it to a much more energetically accessible to remove the electron or move the electrons from one state to the other state. But anyways, that's about it for this particular topic. I hope you're able to understand this and how this will be crucial in order for you to actually focus more on various cycloaddition reactions in organic chemistry using the Fourier molecular orbital understanding. All the same, guys, thanks for watching. Please don't forget to hit the like button, subscribe and share, and see ya on my next video. Have a good day. Peace. Love you all. Bye. And be smart.